welcome everybody. This is my second lecture. So according to the plan, today I will go from Einstein equations that we derived very quickly yesterday, perturbed at first order, through the solution of this equation with the initial condition that we will discuss. Our goal is to understand the matter, our spectrum. That it is something more related to the direct observables that we have, for instance, from galaxy surveys. As we will see, this is not already the thing that we are observing, but it's much closer than, if you want, the curvature perturbation that are generated during inflation. So before I start, let me briefly review what is the matter power spectrum. In general, what is the statistical treatment that we do of cosmological perturbations. So the idea is that, okay, you measure galaxies or matter or whatever traces you have in the sky, and from this you derive some field, for instance, a density field, just to fix the idea, which depends on space and time. And okay, from this you can, as we did yesterday, split it into perturbation plus plus an average value. I do it like this. And actually, we focus now on this density contrast. Okay. As I mentioned briefly yesterday, nobody is able actually to predict the field delta. The only thing we can predict is the statistics of the field delta, and this is what we have to compare with observations. Okay, so what we do indeed is to compute and to measure correlation functions, which in general can be defined, for instance, for an n-point correlation function. They are a function of n space coordinates. And for time, I take, just for simplicity, equal time for each space time, for each special point. And they are defined as expectation values of a product of n fields, where this expectation value, as I mentioned, is an expectation value over some probability distribution function. So this quantity here is just a multiple integral weighted by some n-point distribution function of the product of n fields computed in these n different points. Now, delta 1, delta n is just a shorthand notation for delta x1, delta xn. Okay? And so this is the quantity that we can predict, or we can hope to predict and to compute in such a way that we can compute correlation function in general of all orders and compare them with the observations. As has already been mentioned, the simplest case is when this probability distribution function is Gaussian. So what does it mean? Well, it means basically that for n, for each value of n, it is completely determined by the 2-point correlation functions. Explicitly, a Gaussian n-point distribution function will be given by, so this is delta 1, delta n. Okay, there's some normalization. The square root of the determinant of sigma and the exponential minus 1/2 delta sigma minus 1 delta t. So where delta is just a vector of these n fields computed in n different points, and sigma is the matrix of the 2-point correlation functions, 2-point correlators. It is defined as delta I, delta j. Okay, this is just this, okay, the definition of a Gaussian distribution function. It is to say you have to know only the 2-point distribution, 2-point correlation function for every possible pair of points. And this is the explicit form for the probability distribution function. If this is the probability distribution function, then the result that was mentioned also by Marco Peloso yesterday hold, that is to say, as you know, if you have, say, an odd number of fields, the correlator is 0. On the other hand, if you have an even number of fields, then you can apply big theorem. That is to say, you can express this two n-point correlation function as product of all possible 2-point correlation functions. Okay. For instance, the simplest non-trivial case is just delta 1, delta 2 times delta 3, delta 4 plus the possible permutation. Okay. Okay. But in general, from a given probability distribution function, we can define, as you see, correlation functions. I will mainly deal with the 2-point correlation function, and I will say something about the 3-point correlation function. So let's have a look a little bit closer to the 2-point correlation function. This is just defined. And let me write it as rho x1, rho x2, divided by rho bar square minus 1. Okay. Okay. First observation is that if you assume translation invariance and rotation invariance, then this quantity depends only on the modulus of the distance between the 2 points, so just one variable. And then a few words about the physical meaning or the mathematical meaning of this quantity. Well, the simple way to have a look at it is just to consider the case of a purely random field. That is to say, how can you define a purely random field? You say that the correlation between the density field in 2 points, 2 different points, doesn't have any dependence on the distance of the 2 points. It means that it is just rho x1, rho x2, and due to translation invariance, these two guys, these 1-point correlators, if you want, are equal to rho bar squared. Okay. So this is for a random field. It means there is no particular correlation at any particular scale. The fact that you have a field with a given value here doesn't affect in any way the value of the field here. In this case, you see immediately that the correlation function is equal to 0. So the correlation function can be interpreted as the excess of correlation at a given scale with respect to a random distribution, a random field, or also a defect. Because you see, the correlation function can be even negative, can go down to -1 if you are looking at a scale which you have vacua. The field is empty, basically. So this is the, so in general, this one is can be take values between -1 and infinity. Okay, so this is to understand the correlation, the 2-point correlation function. Then this will be a very important observable, because it provides in reality, in the true observations, it provides a standard ruler. That is to say, a standard length that you know from first principles, I will say. And by computing, by measuring and computing a given feature on the correlation, on the 2-point correlation function, you can basically do cosmological test by observing the galaxy distribution function. I will show it in more detail. Then again, from the real space density field, we can define a density field in Fourier space, something that we will be doing always in these lectures. So let me define it once. My convention, this is the Fourier transform. And with the same convention for the distribution function, you can obtain the power spectrum as the Fourier transform of the 2-point correlation function. So the power spectrum depends only on the modulus of k, of the scale, again, because of the rotation and translation invariance. So this will be our one of our observables together with the correlation functions. And also, from this definition, okay, first of all, you notice that because the field delta is real, then it's the complex conjugate of the Fourier transform is equal to delta of minus k. And this gives you another possibility to define, the definition of the power spectrum in terms of delta k. You can work out by yourself the algebra. Let me do it in one more step. You take the average now in Fourier space of delta k prime, and what you see is, again, because of the assumption of rotation and translation invariance, this is basically, better to say this is just translation invariance. Okay, here is how you read the power spectrum from the average of these fields in Fourier space. You can work out this delta function just to give you a way to directly compute the power spectrum. So you see, what you have to do is to measure the density field in Fourier space, do take the modulus square. This is just a delta function in Fourier space, so this is just the total volume. So you divide by the total volume and you get the power spectrum. Okay, just to say, this is just to say the power spectrum is just delta k modulus square. Okay, keep in mind this fact. Final point, final observation about the power spectrum and the correlation function. Consider now the correlation function in 0. This is just delta, say, delta square, the fluctuation of the density field in a given position. Again, this average is not position dependent because of translation invariance. You apply the definition of the power spectrum, and what you see is that this is and let me write it this way. Okay, I write it this way because this guy here is dimensionless. This is
Massimo, sorry to interrupt you. There is probably if you write slightly bigger is better for the view. Okay.
Sure. Thank you. Thank you for. Okay. So this is the dimensionless power spectrum, something which is dimensionless, and basically what tells you is the real amplitude of the fluctuation on a given scale. Okay. So this is, for instance, what inflation predicts to be almost scale invariant if you look at the power spectrum for the potential, as we will see. Okay, this is everything I have to say for the 2-point function. Remember, this is not for the Gaussian field. This is in general. This is just come from the definition of the power spectrum. What depends on the fact that you can assume Gaussian distribution is the fact that you can use the weak theorem, and basically there is no residual in this case. I mean, the 4-point function is given entirely in terms of products of 2-point functions. Since we are discussing correlation function, just 2 words on higher ordered correlation functions. Okay, the 3-point correlator in the cosmological context is called the bispectrum. You will probably understand why it's bi, even if you have 3 fields. It can be a topic for the discussion. If you want. Okay, you take now the expectation value of 3 fields with 3 different wave numbers. There is again a delta function. Sorry. And this guy here is the bispectrum. And you can realize, again, by using the rotational and translation invariance, that it depends only on the, one way to see it, only on 3 parameters, basically, and you can choose the 3 moduli of the momenta. You immediately realize that this guy is the first signature of non-Gaussianity. If you have Gaussian distributions, these guys to be 0, as we saw a while ago. So this is a guy, the observable that, okay, if you want, the main observable for measuring non-Gaussianity. And okay, you can generalize it to the 4-point function and so on, but I will not use them in these lectures. Okay, so these were basically just definitions. Again, inflation predicts that to a high degree, distribution function of the perturbation generated during inflation is Gaussian. But as we will see, nonlinearities, even the fact that the gravity is a nonlinear theory, produce non-Gaussianity, produce, for instance, contribution to the bispectrum at late times. So if you are interested, for instance, in measuring a possible tiny primordial violation of non-Gaussianity due to the inflation, you will be better, very careful in computing the gravitational effect that we know is there for sure, even if you start with Gaussian initial conditions. Okay, now let me proceed with my program, which was to solve for you the Einstein equations. Of course, what I will do will be a very, very rough solution of a system of coupled differential equations. Actually, you never do like what I'm doing, if not the first time, to understand what's going on. There are very good codes, very widely used, that solves exactly the linear equations in full general relativity. To give you just two names, you can look for Camb or Class. They solve exactly the equation that I wrote yesterday by employing also the Boltzmann equation for photons and neutrinos when needed. Okay. But okay, just to give you some flavor of what's going on with these equations, let's go back to the equation for the gravitational potential that I wrote yesterday as last equation. So phi is called the gravitational potential because, as you remember, it's the guy who solves this relativistic Poisson equation that I will also use in the future. Okay, this was the equation. Delta P is the fluctuations in pressure, the pressure fluctuation. So the first thing I will do will be to express this pressure perturbation as a delta rho times this ratio. And this ratio is called the adiabatic sound speed. And it is a good approximation for many fluids to assume that it is scale independent, but time dependent in general. And for matter, this is 0. And for radiation, it is 1/3. It is to say, it's like the equation of state. Okay, so now the program is to write this equation in, during the matter domination and the radiation domination era, and to see what happens at different scales to the solutions of these equations. So let's look before at matter domination. So matter domination is defined basically by CS square equal to 0 in this case. So there is no pressure. This is the fundamental property of what we call cold dark matter, which differentiates cold dark matter by with respect to baryons, for instance, at least as long as baryons are coupled with the photons. So this is the defining, if you want, property of cold dark matter. And what you have also to know about matter domination is something that we have seen yesterday. That is to say that H square is dominated by raw matter times A square. So this scales as A to the -1. Okay, H square is the Hubble parameter that I'm using, that is the one defined with respect to conformal time. Okay, so because of this, you can also check that 2H dot is equal to minus H squared during matter domination. So you see this guy, this coefficient is equal to 0, and the equation simplifies dramatically. Okay. Okay, you immediately find the solution. Phi dot equal to 0, I mean, phi equal constant is a solution, okay? If you do things a little bit, harder, first of all, you recall that H is equal to 2 divided by tau during matter domination, so this equation is 6 over tau. And then you can find, okay, this is a second order differential equation, so there are two solutions. One is phi constant, the other one is phi that decays like tau to the minus phi, okay? So this is what is called the decaying mode. That basically, the linear order has no relevance in cosmology because as time passes, the potential only, I mean, even if you start with a mixed initial condition, then as time passes, the decay mode becomes less relevant, and you asymptotically tend to the constant solution, which is called the growing mode. Okay, now let's keep in mind this equation for matter domination. I'm sorry, I'm going to write on the same blackboard just to keep the two results on the same page. So for radiation domination, during radiation domination, what you have is that, okay, CS squared, we already said this is 1/3. And the other property is that H dot is equal to minus H squared. Okay, then by using the equation that I just wrote plus the Poisson equation, so the equation that I just wrote was the trace equation, and then combine it with the Poisson equation. I don't give you the detail. If you want, I can give. I mean, I will leave you the notes at the end of the lecture, so you can check yourself. Let me skip some passage. What you have is an equation of this type. In Fourier space. Okay, this is the same both in Fourier and in real space. Basically because there are no Laplacians here left. On the other hand, if I go in Fourier space, this equation the equation during radiation domination is this one. So the first thing that we notice is that this equation is scale dependent, depends on k, on the wave number. Whereas during matter domination, we have this behavior everywhere, at all scales. There's no horizon here. I mean, the other relevant scale, of course, you can imagine is the horizon, which gives you the time dependence of the background. And here there's only the scale. Here there are two scales: the scale I'm looking at and the horizon. So I can imagine that the solution of this equation will depend on the scale. And actually, okay, I solved them for you. The solution is, okay, again, here there are two solutions because it's a second order differential equation, but I select the solution which is regular in tau, the limit tau to 0. And what I get is an oscillating solution which depends on y, and y is defined as k tau square root 3, square root of 3. It is also k over h square root of 3. Okay, so you see, sorry for the busy blackboard, but okay, you see that the behavior of the solution depends on y. So it depends on whether you are on super horizon scale or sub horizon scales. And to summarize, what we have is that if you are super horizon, that is to say k over h much less than 1, I'm looking at scales which are much larger than the Hubble horizon, the solution is simply a constant. On the other hand, on sub-horizon scales, the solution is oscillating, but with a decaying amplitude. Okay? What matters here is really that, okay, there are oscillations with the frequencies which is just given by k over the square root of 3, but for the moment, just focus on the fact that there is a decaying in time as tau square, okay? And all this oscillatory behavior comes, again, from the speed of sound that is here.
Massimo, there is a question.
Yes, please. Please.
Hi, thanks. Yeah, I might have just missed this, but did you oppose a boundary condition?
Sorry, I couldn't hear you. Can you speak
sorry,
slowly?
can you hear me?
Yeah. Can you
Can
repeat?
you hear me? Yes. I might have just missed this, but did you impose a boundary condition?
Boundary conditions. Very good. Now, for the moment, I didn't discuss the initial conditions. I will give a discussion in a while. But of course, this is the relevant point, because remember, we want to match these solutions with the initial conditions that come from inflation. So the game is exactly what you are saying. Now I'm discussing general solutions, but then I have to specify the initial conditions. Okay?
Got it.
You will see, and then maybe you can ask again. Okay, so this is, I was saying about a few words about the physics. You see there is now pressure in this photon fluids, and basically pressure prevents compression due to gravity. We will see again this mechanism playing a role in oscillation in the baryonic photonic fluid before recombination. But this is again the first and the main difference between cold dark matter and radiation and whatever it is coupled to radiation. Okay, so to summarize, the behavior during matter domination, we have basically a constant potential before and after the entrance in the horizon, I mean, both subhorizon and superhorizon. On the other hand, during radiation domination, a scale remains constant as long as it is larger than the horizon and becomes to decay. The perturbation on this scale becomes to decay once it enters the horizon. The reason why, in both cases, the perturbation stays constant outside the horizon is exactly what was also mentioned yesterday. It's just causality. Even if there are I mean, some physics going on at a short distance, I'm considering a scale which is so much larger than the horizon that no causal process can modify the behavior of this perturbation on such a large scale. Okay, so to summarize and to learn what is the lesson that we learn from this discussion, again, let me go back to this plot, okay, in which I have here co-moving scales. If you want, I can design them like 1 over k, the wave number, or if you want L, which is the Fourier transform. And as you remember, there was, I mean, the relevant curve to follow here is the horizon, which in this unit is just 1 over h, okay? So there is this knee here, which is this is the logarithm of the scale factor. And here we will consider the behavior of different scales, okay? So in this plot, there was a question yesterday, what is the meaning of these horizontal lines? So basically, you are putting a label on a given scale. This is the scale that, for instance, today is something like 100 megaparsec today. And then you know what it was before, simply because you just do a naive scale factor multiplication. And if you want, this one was the scale that was, say, 10 megaparsec and so on and so forth, okay? So you see immediately that there is some there is a particular scale here, the one corresponding to the knee. This is the scale which re-enters the horizon exactly at matter radiation equivalence. So this is the scale factor, or the ratio, if you want, at equivalence. It means that you are here in radiation domination, and here you are in matter domination. So you have a first separation of scales between those who enter the horizon before radiation domination, and those who enter the horizon after radiation domination. Okay. So this scale I will call K equivalence, which is just given by the values of the Hubble constant at equivalence. Now let me follow the history, if you want, of two different scales. One that I will call K1. K1, you see, it enters the horizon after the equivalence. It means that K1 is much lower, say, than H equivalence. And K2, on the other hand, will enter the horizon before the equivalence. So we'll call it, I mean, this will be much larger than H equivalence. And okay, let's start from the easy part. Consider K1. K1 was outside the horizon at the beginning. This is already one first element about the initial condition. I will give it the initial condition deeply during the radiation domination phase for all the scales I'm interested. So follow K1. It is constant here because it's outside the horizon. I mean, the potential on the scale K1 is constant. Let me write it. Then it enters the horizon, but when it enters the horizon, we are already in matter domination, so it's constant again. So the morale here is that phi k is constant either both before and after the horizon entry. Okay. On the other hand, let's follow K2. Okay, K2 is the potential in K2 is constant here. Then at some point, which we call AK, if you want, AK is the epoch at which the scale, sorry, AK2, the scale K2 enters the horizon. Or if you want, at K2, at A2, the Hubble horizon is equal to K2. The Hubble parameter is equal to K2. And here, what happens is that the scale, as we have seen, starts to, the potential starts to decay as A to the power -2. So you have a decay of the potential as AK over AEC to the -2. I mean, the decay starts here and ends here during equivalence, because after equivalence, the potential is constant again. So with respect to this scale, where we have no depletion, no decay of the gravitational potential, we have a decay here which goes as the ratio between the scale factor at the time K2 and the equivalence scale factor to the power -2. Okay, so the earlier the scale enters the horizon, the more depleted it is with respect to the initial conditions. This is the whole story, basically. A zero-order approximation.
there is a question.
Yes, please.
Quentin, you can speak.
Yes, thank you. Hi. Now, why in the meta domination? I mean, when the mode enters meta domination, it doesn't behave like the decaying mode, but it will be constant.
Why doesn't decay? Is it the decay mode? Is this the question?
Yeah, I mean, we had two solutions in the meta domination.
Yeah, okay. There are two solutions, but even if you start with a combination of the two solutions, the components which is in the decay mode will decay. So after a short cosmological time, you will end up only with the constant mode, with the growing or constant mode. Okay. This is in general. I mean, you start with a combination, if you want, alpha const plus beta dec. Okay, you wait some time. After some time, this one is decayed. Start with -5. This one is constant. So you end up in the constant mode. Okay? So you don't need actually to, at the linear level, you don't need to follow the decay mode. Actually, as you go nonlinear, since everything gets mixed up, you will see that also the decay mode is very important, but not at this level. Tomorrow and the day after tomorrow, you will see how the decay mode enters. Is it okay?
Yeah, okay, thank you.
Thank you. Okay, so just to summarize again, sorry, phi of K1, where K1 was the scale larger than the horizon, is constant. That phi of K2 decays as AX divided AK2 to the power -2. Then you remember that during, and this happens during radiation domination. During radiation domination, H square goes like H to the -2. So it means this ratio is also HX divided by HK2 to the power 2. Okay? And HX and HH2 are exactly defined as the value of the Hubble parameter when either the KX or K2 enter the horizon. So this is also expressible as KX over K2. So phi of K2 decays as K2 squared for K2 much larger than KX. This is constant for K1 much smaller than KX. Okay? Okay, let's, I mean, keeping in mind this, this behavior, now we can discuss briefly the initial conditions, then we put everything together, and we will finally get to the matter power spectrum. Okay. Okay, I just deleted the plot that I will use again. Okay, now, how do you set the initial condition? First, you decide the range of scales that you are interested in. Let's say I'm interested in this range of scales, of comoving scales. Then I set the initial condition at some time, initial time, or redshift or scale factor, such that all these scales are deeply inside the horizon. Okay? Outside the horizon, sorry, deeply outside the horizon. All these scales are much lower than H, at the initial time in for all the interesting scales. And also, A in is well inside radiation domination. So it's well less than the scale factor at radiation domination. Okay? And what gives me the initial condition is the cosmological perturbation generated at inflation. So basically, here at this initial time, I do the matching between the initial condition for the late time evolution of the perturbation with the conserved gravitational potential generated during inflation. Okay? Mode by mode, I read the information which comes from the primordial epoch of inflation, and I match it to my initial conditions, and then I'm ready to evolve in the late time. Okay, there is a tiny complication here, which I will not spend too much on. It is to say, but I will just mention it. I told you that the gravitational potential is conserved outside the horizon. This is not exactly true. It is constant outside the horizon, but it's not always conserved, because the conserved quantity is actually a related one. Okay. Well, phi is the gravitational potential that we have considered up to now, and Q is the scalar component of the momentum perturbation. And R, this quantity is called the co-moving curvature perturbation. Okay, the only important point is that this quantity is conserved outside the horizon at every epoch, matter radiation. And so this is the quantity which directly brings you the information from inflation. So what I have to do is to find the relation between this and this. And I will do it, I will just give you the result. Minus. Okay, so you see, when the equation of state of the background is constant, phi is constant as R of k, but if there is a variation of the gravitation of the equation of state of the background, like we have at equivalence, while crossing equivalence, this one stays constant and this one doesn't. So the end result is that you have a variation of phi k during the radiation domination and the matter domination. This one, both this one and the conservation of this one, you can prove by using the Einstein equations that you have already. Okay, this is just to say that the logical process is, okay, you get the initial condition for Rk from inflation, you translate them in initial condition for phi k, and then you run your system of equations. Okay. But the point is that you have also other fields, other fluids, and other fields in the problem. Not only the gravitational potential, but also the density contrast of all the different species: radiation, matter, baryons, neutrinos. So one question is, how do I set the initial conditions for these other fields? And the answer is you set them according to, with the property of being adiabatic. What does adiabatic initial condition mean? So the point is that for every fluid, say a fluid with the equation of state W, you have this combination which is directly related to the initial condition, at the given scale k, the initial condition from inflation. So you see, for radiation, you have 1/3 here. For matter and baryons, you have 0. So this gives you different coefficients in front of this delta. But apart from that, all the different initial conditions are fixed. So if you think a little bit, this is really fantastic. I mean, if you have an overdensity, for instance, in photon, and you are sure that in the same region you have an overdensity in baryons, matter, and whatever else, simply weighted by this 1 plus the equation of state. So where does it come from? How can it be possible? I mean, it is called a diabatic initial condition. But it turns out, if you want, I can give you some more details, but it's a very short discussion, that it is a prediction, this kind of initial condition, that for every W, you have the same initial condition weighted by 1 plus W, is a prediction of inflation when you have a single clock. As Marco repeated many times, the inflaton field can be seen as a clock. So if you have just one field that sets the time, if you want, to the end of inflation, then we are calling this situation single clock inflation. And in single clock inflation, you have the same initial condition for all the different species. Okay. If you have questions, please ask now or in the discussion. The only thing I can say is that you can see all this perturbation as...
There is one question.
Yes, please.
Hi. The moving curvature perturbation, did you say that is observable?
Well, you observe when you are inside, when it is inside the horizon. No, I didn't say that it is observable. I said it is conserved.
Ah, it's conserved. Ah, okay.
Yeah, sorry.
No, I misunderstood. Thanks.
Yeah, because I was starting with a long discussion, but probably it was just something that you that was not clear on the audio. Okay, so now everything is set. We read this from inflation. We are able to set initial condition for all the species that I have in my coupled system of differential equations. And I can go directly through the computation of the matter power spectrum. Okay. To do that, so what I'm interested in is the power spectrum of delta, or if you want, of matter, scale K, which is basically related, as you see, as I discussed, to delta K modulus square for matter, okay? So now I have to relate delta K of matter to the gravitational potential and to the initial conditions, and then I have the answer to my problem, okay? To do that, I use, again, the Poisson equation. If you remember, we had an equation in which the Laplacian of the potential is given by 3/2 h squared, a big delta. And this big delta is actually related to delta matter, to delta. Okay, that big delta was 3hq over rho. And now, believe me, if you are going to look at this perturbation sub-horizon, because we are going to observe it, so it should be sub-horizon, so for k much larger than the horizon at late time, we are observing this perturbation today. This is just the density perturbation in matter, corrected by, again, if you want, relativistic correction of order h over k squared. Okay, so the smaller, the deeper inside the horizon, the more this quantity is the matter density contrast. So again, so here I have directly a relation between delta and phi. In particular, delta k at some epoch a, identified by some scale factor a, is just minus 2/3 k square. I transform the Laplacian in a minus k square in Fourier space, h square phi of k, okay? At the same epoch a. So now I have to use my lessons, what I learned about the time evolution of this potential at the scale k from A, you can imagine that it is close to 1, is today, back to A initial. And then I am done. Then I'm done. I give you, okay, the result. It is k square over h square. Then I will express all the time evolution in this way. This is the initial condition, if you want, for the co-moving curvature perturbation at some very early time, which is constant, so I can remove initial. And here I have a function, k, or say, better to say, a function of k over k equivalence, which gives me, takes into account this different behavior of the wave numbers which enters the horizon before or after equivalence. And then again, I have a 2/5 here, which is just a consequence of this matching between R and phi. Okay, this is not important. So in this solution, in this equation, this solution, you have basically everything. So this is the primordial. This is the input between from the primordial initial condition. This is the effect of the causal evolution that changes the aspect of the perturbation when it enters the horizon. So if you want, this is the causal evolution. In matter and radiation domination. And finally, notice that neither of these terms depends on time. The time dependence is given, okay, basically, is given by this 1 over h square, which is A if you are looking at this power spectrum at late times, that is during matter domination. Okay? So what is this transfer function? It's just a function which goes to 1 as k is much smaller than k equivalence, and to 1, sorry, to kx over k to the square for k much larger than k equivalence. Okay? It dumps the fluctuations that enter the horizons before matter radiation equivalence. Okay, now we get the power spectrum simply by squaring this guy. So what we have is pi delta, that if you look at it at sub-horizon scales, it's just let me put time here, is, okay, the square of that guy there. So is, okay, proportional to k to the 4 divided by h to the 4, t square of k, and the primordial power spectrum of the co-moving density perturbation, which is just a function of k. Okay. So what is the prediction from inflation on this guy? The prediction from inflation is that this guy divided by 2 pi square, yes, PR of k, which is the dimensionless power spectrum, is simply given by some amplitude that we call AS, k over some pivot scale that we can fix, I mean, conventionally, times this ns minus 1. Ns equal 1 is an exactly scale invariant spectrum, and ns less than 1 is what you expect in slow roll inflation, and this is also what you measure, for instance, on CMB. This ns is something like 0.655. Okay, and the AS also is known once you fix the K0, which is just a convention, is something of order 10 to the minus 10, also known with very good precision. So now you plug this into the power spectrum. So what you see is that the power spectrum goes as 1 over, I just put the main dependencies, k to the ns for k much larger than k equivalence. And then you have a damping by k to the power 4. So you have 1 over h4, k over ns minus 4 for k. Sorry, this was much less, and this is much larger than kappa ek. And everything is growing in time as 1 over h to the power 4 in this approximation in which we have only matter in the background, on the background. So let me plot it. So you have at very large scales, low case, you have just the power law that it is predicted by inflation, k to the ns. Then you have some turnaround at some point, and you understand that this turnaround is exactly at k equivalence, the scale which enters the horizon at the matter radiation equivalence. And then you have an inversion. Here it goes again in this approximation as ns minus 4. And the whole thing is growing in time as, okay, in this case, as a square. Okay.
There is a question.
Yes, please.
Hi, thanks. Is there an intuitive way to understand why that PR goes like 1 over h to the 4th?
This one, this minus 4 here. Yes, because this comes from h to minus 4, you are saying.
Yeah. Mm-hmm.
Yeah, if you remember, this comes from the Poisson equations. No? You have the Poisson equation. Okay, let me write it directly in Fourier space. You remember this equation that I wrote before? Now, we are interested in delta of k. Then it goes like 2/3 k squared over h squared phi k. Okay? And then you get the power spectrum. So you square this coefficient here. So you have k to the power 4 divided by h to the power 4. This is the origin of this h to the power minus 4. Is it okay?
Got it. Okay. Yep. Thank you.
Okay. Okay, let me just put some scales, just because later on we are going to discuss where this approximation is okay, where the nonlinearities start to become important. So K equivalence, I invite you to do this computation. K equivalence, first of all, you should find out what you need to do this computation. But K equivalence is something like 0.012, 15, H inverse megaparsec. Where this H is, again, a historical, I mean, I measure scales in Fourier space. I can measure them either in 1 over megaparsec or in H over megaparsec. You have to just choose one convention. But this H is just the ratio between the measured H and 100 kilometer per second per megaparsec. So it's a way to megaparsec. It's a way to parameterize our ignorance on H. But okay, this small h is now, at least from CMB data, is determined very well. Even if there are some tensions. Okay, but for the moment, let's say that we know it very well at this level. Okay, this is the scale where there is the turnaround. Then another important scale, what is the horizon today? I mean, what is the part of this potential, of this power spectrum that I can observe? Again, let us call it K naught. It is something of order 10 to the minus 4 H inverse megaparsec. Okay? Okay, at this point there are no more features in this power spectrum. So at this approximation, which I basically have in the background only matter. So this is an approximation in which omega matter, which is rho matter divided by rho total, is equal to 1 today. Okay. Then I will show you what changes if you take into account, as you should, the fact that omega matter is not 1 and other effects that modify a little bit this result and gives to them to it some more structure. How much time do I have? 15? Yes. So okay. Let us correct a little bit. Okay. These are not irrelevant corrections. They are really crucial if you want to do cosmology. So I mean, my treatment was just to show you basically where this behavior can come from, but there are some relevant corrections on which I will now list. First of all, related to last question, time dependence. So the result that we had 1 over H4 exactly depends on the fact that we are in an approximation of omega matter equal to 1. So what happens if we have a more, realistic background, which is the one in which we live? So what happens if omega matter today is given by, say, rho matter divided by rho matter plus rho lambda, where, as you remember, rho goes like h to the minus 3, and lambda, if it is a cosmological constant, is constant. It means that this omega was 1 earlier, but now it's becoming less and less than 1. So it will change the growth of the perturbation. I will not do all the computation. I just give you again the sketch. You now follow, you can do it many ways, okay? One way is just to follow the perturbation equation for matter. I specified the equation that I wrote before for the matter density and velocity field. Where, what is theta? Theta m is just defined as the divergence of the peculiar velocity field, okay? So it's a scalar, which basically at first order perturbation completely defines the velocity perturbation. And again, if you couple this to the Poisson to the Poisson equation, and then you go sub-horizon today, you can combine these two equations plus the Poisson and get an equation which I will just write and comment on a little bit. Okay. So again, it's a so this is this is the equation for delta m. You see there are two pieces as usual. One is the damping due to the expansion of the universe, while the right-hand side comes from the Poisson equation. And as you see, the fact that not all the energy density of the universe is in matter enters through this omega m factor, which is 1 very early on, now today is decreasing. So this changes the behavior of the perturbation. Also, h square depends on omega m, because h square, if you remember, is proportional to the total energy density. And if you simplify and say that you have just matter plus radiation, plus, sorry, cosmological constant today, because radiation is becoming irrelevant energetically, then this is again, okay, this again goes as a to the minus 3 when matter is dominant, but is going to decay as to become constant when the cosmological constant become constant. So the ratio between rho matter and rho lambda enters both in the damping, in the time dependence of the damping term, and in this omega m. Okay. As a result, the growth of the matter perturbation, which was A, grows like the scale factor during matter domination for m equal to 1, goes to some function d of A, which is different from A, which is called the growth factor. That you can compute from this equation. You can also have analytical solution to this equation. What is the main feature? Well, the main feature is that as soon as the energy density of the cosmological constant starts to become important, the growth of perturbation is stopped. And the reason is that this source term, this omega m, is going to disappear, and so there is no more source in this equation, and the growth of delta m will decrease. Okay, so this a square dependence that I computed before, and also I defended in a question before, actually is to be replaced with some d square growth factor. And the relevant point is that depending on the nature of dark energy, this stop, I mean, this slowing down of the growth of perturbation will become earlier or later on. You can understand it very simply, I think. So if this is the logarithm of rho, and this is again logarithm of A, now matter goes as a to the minus 3. Now if you have a cosmological constant, it goes as a constant. Now assume that you fix today the ratio between this number, and you change the nature of the dark energy. Instead of being just a W equal to -1 field, it can be a field with a slightly larger W. And what you see is that in this case, the equivalence between matter and the cosmological constant appears earlier, and so the stop of the perturbation, the growth of perturbation appears earlier. So a potential way to measure the equation of state is actually to look at the growth of the perturbation and see if it is reproduced by cosmological constant or by something with a different equation of state. Okay. Okay, let me start. I have 5 minutes more. Okay, so I will now, so this was the first modification, the first structure that I changed a little bit in this diagram. Now I'm going to talk about another modification. I will just give you first the final result, and then I will motivate where it comes from. Actually, here what you have are two boring power laws, k to the ns and k to the ns minus 4. Actually, the real matter power spectrum has some very interesting and important structure here that are some oscillations, okay, that I exaggerated here just to show you in the plot, from scales of order 0.05, and then they are damped a little bit. So these oscillations are called baryonic acoustic oscillations, BAOs. And they are very crucial for us, for present-day cosmology, because they appear at a scale which is known, say, from first principles, and it is in the measurable range of scales with present-day galaxy surveys. And so it provides you a landscape that you can measure in the sky, and through which you can reproduce the expansion history of the universe by measuring the scale at different redshifts in a way which is completely independent, for instance, for other ways in which you reproduce the growing expansion history of the universe, for instance, this supernovae 1A, or which is basically the other method. Okay, so I now will start a little bit to discuss these BAOs, where do they come from, and maybe tomorrow we'll show you some some plots. Okay, baryonic acoustic oscillation, as the name tells you, depends on the fact that you have not only colder matter, but you have also baryons in the game and photons. So let's now step back to the epoch in which baryons, that in cosmology means protons and electrons and also neutrons, so baryons and photons were tightly coupled. I mean, we are before recombination. Before recombination, so electrons are free, are not bound to protons, and so basically Thomson scattering keeps the electron fluid and the photon fluid tightly coupled. So when there are overdensities in one of the two, the other one follows, and so on, as so forth. And of course, the baryons have to follow the electrons, because otherwise there will be electric fields. I mean, because the full fluid is electrically neutral. So as a result, not only the electron, but also the baryons, the true baryons, the protons, form a single fluid. So that means practically that you can study the equation for delta gamma. And this is exactly equal to the equation for the baryons, which means the electrons and the protons. Okay, so this equation for delta gamma, which I give to you, is again a second order differential equation. I will not derive it. If you want, I can give you more details. Okay, we have another R here. We have many R's in this business, but it is a different R from the one. This is not the co-moving perturbation. I will tell you in a while what it is. Okay, so this equation is again on sub-horizon scales. So I forget general relativistic corrections. What you have here is, okay, if you just look at the left-hand side, you have some damping term, and you have again an oscillatory term, a pressure term, which depend again on the speed of sound of this fluid, okay, times k squared. And on the right-hand side, you have the gravitational potential. So this is in Fourier space. And you see that this basically is the equation of motion of a damped forced oscillator, because there is an external force which drives the oscillations, and then there is some damping and some speed of sound. So what is R? R reminds you that you are not looking only at photons, but you are looking actually at baryon photon fluid. So R is just given by, okay, 3/4, the ratio of baryons with respect to the ratio of photon. And if you want some numbers, it is 0.6. Okay, omega baryon h squared divided by 0.02. But the important point is that it grows as the scale factor. So it's something that, okay, normalized here to 10 to the 3 because we are, decoupling is actually 10 to the 3, 10 to the minus 3. So at decoupling, this is something over the 0.6 if omega baryons is of this order. And then it grows because baryons are becoming more important than photons. And the CS square is not just 1/3, but again depends on this baryon to photon ratio. Okay, so we have oscillations forced by the gravitational potential. So that you have to imagine that, okay, inflation basically sets the shape of the gravitational potential. Then as the scales starts to enter the horizon, they feel the potential wells which were laid down by inflation. They start to oscillate. Gravity wants to squeeze them, and pressure opposes this squeezing. So what you have is really acoustic waves with a speed of sound of this order, which makes the big difference, again, between baryons and dark matter. Maybe I close now, but with a final sentence. If somebody tells you that dark matter, the origin, the evidence of dark matter is some galaxy rotation curve or something like that, forget it. For me, for me, it is really this equation: the fact that baryons do not have time to grow as they enter the horizon before decoupling with photons, whereas what we call cold dark matter has 0 speed of sound always, and so it starts to grow as soon as it enters the horizon after matter radiation equivalence. And this changes a lot the structure of the perturbation with respect to what you would have without any cold dark matter. So I can close here. There are questions?
I don't see any question at the moment. Maybe we want to save them for the discussion session.
Okay.
Okay, so we can pause here and we reconvene later for the lecture of Marco. Okay, thank you very much.
Thank you.